Good afternoon. I am Dr. Vivek Kumar Sharma, Professor in Mathematics at Jagan Nath University, Jaipur. I am going to present a lecture on differential equations. All of us know this whole world is changing rapidly. Everything is changing at every moment. The great dance of the celestial bodies is going on. The earth is revolving around the radiant sun, and we can find the space and time coordinate of each and everything is changing very rapidly. So, change is a very important fact, and rate of change is very important in industry and the business sector. As for example, bankers know what is the rate of inflow, what is the rate of outflow, increase in the income, decrease in the production, and decrease and increase in the sales. So, rate of change in dependent variable with respect to the independent variable is known as the differential coefficient, and an equation that contains the relationship between dependent variable and its derivative is known as the differential equation. So, differential equation we can define as the equation that has a function and its derivative. Examples of differential equations are y minus x into x dy by dx equals to a square into y square plus dy by d. Similarly, 1 plus x plus y whole square dy by dx equals to 1 is again a differential equation. D square plus d minus 2 into y equals to x plus sin x is again a differential equation, where capital D is identical equals to d by dx differential operator. Importance of the differential equation, we will discuss some important fields. It is used in modeling the complex systems, predicting and analyzing the dynamic processes, engineering designs and optimization, control systems, signal processing, and most importantly mathematical modeling of physical and fundamental laws of the nature. So, we can say differential equation provides a powerful mathematical language for describing, analyzing and predicting a wide range of the phenomena in scientific and engineering disciplines. Classification of differential equation. We can classify the differential equation in two parts. One is ordinary differential equation ODE and other one is partial differential equation PDE. Ordinary differential equations are the equations involving a single independent variable. For example, d2y by d of x square minus 4x dy by dx plus 4x square minus 1 into y equals to minus 3 into e to the power x square sin 2x. Okay. So, this is a ordinary differential equation. Since this equation depends only a single variable x, independent variable x, y is the dependent variable. So, we can say this is example of a ordinary differential equation. Partial differential equations are the equation involving multiple independent variables. For example, del 2u by del of x square equals to del u by del t. In this equation, differential equation, u is the dependent variable and x and t are independent variables. So, number of independent variables are more than one. Therefore, this differential equation is a partial differential equation. Another example of the partial differential equation is del z upon del x minus del z upon del y whole square equals to 4 times of 1 minus del z by del x minus del z by del of y. Now, we come to the some definitions of differential equation. We are going to define the order and degree of a differential equation. By order of a differential equation, we mean that order of highest order derivative present in the equation. So, we can say order of a differential equation is nothing but the order of highest order derivative present in the differential equation. Okay. For example, if we want to know through the example, consider this equation 1 plus x plus y whole square dy by dx equals to 1. Here we can say the equation contains a derivative dy by d of x, that is of the first order. So, we can say the order of this differential equation is first order, or equation is first order equation. Similarly, in the second case, second equation is d2y by d of x square minus 4 dy by dx plus 4y equals to minus 3 times of e to the power x square sin 2x. Here we can easily observe that the equation contains highest order derivative as d2y by d of x square. Its order is 2. Therefore, the order of the differential equation is 2, or we can say this equation is second order differential equation. Similarly, in the last equation, we can again observe that the equation contains highest order derivative is of second order d2y by d of x square. That is why it is again a second order differential equation. Now, we are going to define the degree of a differential equation. So, degree of a differential equation can be defined as the power of highest order derivative which occurs in the differential equation, provided the equation has been made free from the radical and the fractional signs. Okay. So, for the example, I take the equation number 3, that is rho is equals to 1 plus d2y by d of x whole square 3 by 2 divided by d2 by d of x square, well known formula for the radius of curvature. If we simplify this equation, or we make free from the radical sign 3 by 2. So, this equation can be written as rho square into d2y by d of x square whole square equals to 1 plus dy by dx whole square to the power 3. So, we can see that the highest order derivatives power is 2. Therefore, equation is of degree 2. So, in this way we can define the order and degree of a differential equation. Now, the linear differential equation, we will discuss the linear differential equation. Differential equations in which the dependent variable and their derivatives occurs only in first degree, and the equation does not contain any cross multiple terms. In that case, we say this equation is known as the linear differential equation. For example, d2y by d of x square plus dy by dx minus 2y equals to x plus sin x. Here we can easily observe that the first term power is 1, since d2y by d of x square power is 1 plus dy by d of x power 1 and plus 2 times y's power is also 1 is equals to x plus sin x. So, we can observe that the dependent variable and their derivatives are having the powers 1 only. Therefore, this is a linear differential equation or example of linear differential equation. Now, we wish to know what is the meaning of solution of a differential equation. So, solution of a differential equation is nothing but the relation between dependent and independent variables which satisfy the given equation and also does not contain any derivative term. So, there are two types of the solution, one is the general solution, other one is the particular solution. General solution of the differential equation is that in which the number of independent arbitrary constant are equal to the order of differential equations, and the particular solutions are obtained by assigning the particular values to the arbitrary constant in a general solution. So, we can easily define the two types of the solutions of the differential equations. Now, or in this class we mainly study the first order and first degree equations. Solutions of all first order first degree differential equations are cannot be found, but some particular type of the first order first degree equations can be solved. The general format of first order first degree equations are f1 xy, it means function of some function of xy dx is equals to some function of xy into dy, or a differential equation of the type dy by d of x is equals to some function of xy divided by some function of again xy. So, here we can observe this equation contains a derivative of the first order, that is why its order is first and its power is 1, therefore, its degree is also 1, that is why this is the general format of the differential equation. So, Now, in this class we will discuss only the two methods to solve this first order first degree equations in which we can separate the variables dependent and independent variables on the two sides of the equality of the equation. So, that comes under the variable separable problems, and another kind is homogeneous differential equation. Although the first order first degree equation can also be solved for the category linear differential equations, equations reducible to the linear differential equations, exact differential equations, or equations reducible to homogeneous form, and equations reducible to the exact equations. So, particularly we are going to study the first order first degree equations which are of the in which we can separate the variables. Variable separable form, the general format of variable separable forms equation is some function of x into dx is equals to some function of y into dy. On the next step, when we separate the variables, then we can easily integrate the both sides of the equation and include a constant of integration. So, finally, we get the solution of differential equation. This is the this will be the general solution of the differential equation. Examples: suppose we have to solve a differential equation e to the power y plus 1 cos x dx plus e to the power y sin x dy equals to 0. And if we wish to solve this equation, then solution of the equation number 1 here. Here we can easily observe that we can separate the variables y on one hand and variables x on the other hand. So, this can be done by dividing the whole equation sin x into e to the power y plus 1. So, we have the form cos of x upon sin of x on simplification is equals to minus times of e to the power y divided by e to the power y plus 1 into dy. So, we can easily see that the variables are separated, the terms or functions of x are lying on the left side and the functions of the y are lying on the right side of the differential equation. Okay. So, if we wish to find out the solution of the equation after separating the variables, what we have to do? We have to just integrate these two equations on both sides. So, integrate on both sides of this equation and put a constant, arbitrary constant or constant of integration. Now, we can easily see that the integration of this left hand side term is nothing but log of sin x is equals to minus sign as it is, then log of e to the power y plus 1 plus constant of integration, as sin x derivative is exactly present in the numerator part. So, integration of f dash x upon f x dx is log of f x. By using this formula, we integrate the equation 1 easily. Similarly, we can solve the equation number 2 by method of variable separation method. We rewrite the equation, or if we observe this equation for separation of variable, we can easily observe that if we divide this equation whole equation by 10 y and 1 minus e to the power x. So, variables can be separated. On dividing these two required terms, we get the resultant equation as 3 times of e to the power x divided by 1 minus e to the power x into dx is equals to minus times of sec square y dy divided by 10 y. Again, we can observe that we have separated the variables x on left hand side terms and the functions of y and derivatives are on right hand side terms. So, just we have to integrate on both sides and we have to put a constant of integration. So, applying the integration concepts, the equation solutions of the given equation now becomes 3 times of minus 3 times of log of 1 minus e to the power x is equals to minus times of log of 10 y plus constant of integration. Now, the second form homogeneous differential equations. Homogeneous differential equations are again first order first degree equations. General format of this equation is dy by dx is equals to some function of x y homogeneous function divided by some function of g x y again homogeneous function, f and g are homogeneous functions. Okay. So, in this type of equation algorithm to solve this equation is nothing, just we have to assume that y is equals to v x. If we assume y equals to v x and we differentiate this, then we have dy by dx is equals to v plus x dv by d of x. If we assume this or label this equation, first equation as number 1, assumption as number 2, equation number 2 and derivative term is number 3. On substituting the values of y and dy by dx from equation 2 and 3 into the 1, the equation number 1 becomes v plus x dv by d of x is equals to some function of x v x and similarly some function of x and v x. Now, the x terms can be cancel out from numerator and denominator term in the right hand side, and then this equation number 4 can be reduced in the variable separable form, which we have studied just now. So, we can easily find the solution of this type of equations. So, for the example, I am going to take one differential equation first order first degree and check how we can solve or get the solution of this equation. So, solution of equation 1. First of all, I have to write in the proper format, equation 1 in the proper format. This can be written as 2 times of x y dy is equals to x square plus y square into dx. Then, if I divide the equation x square plus 2 x y on both sides, then get dy by dx is equals to x square plus y square divided by 2 times of x y. So, here we can easily observe numerator term is of degree 2 in x and y and denominator term is again degree 2 in x and y. So, this is homogeneous numerator and homogeneous denominator, that is why it is a homogeneous differential equation of order 2 or degree 2, first order first degree equation. So, to find the solution of this type of equation, we have to substitute some assumptions which we have made earlier, dy by dx equals to x square plus y square upon 2 times of x y. So, just assume y is equals to v x, so that dy by d of x becomes v plus x dv by d of x. Now, substitute these assumptions in the given differential equation. We have v plus x dv by d of x is equals to x square plus v square x square divided by 2 times of x into v x. If we take x square as a common from numerator term, then we have x square into 1 plus v square divided by 2 times of x square into v. So, x square will cancel out with each other. Finally, we have v plus x dv by d of x is equals to 1 plus v square upon 2v. Now, we will separate the variables at this stage. So, we can say x into dv by d of x is equals to 1 plus v square upon 2v minus v. On taking the LCM, we have 1 plus v square minus 2v square divided by 2v. Ultimately, we have 1 minus v square upon 2v. Finally, we separate the variables. We can write it as 2v upon 1 minus v square dv is equals to dx upon x. So, ultimately the given equation reduced in the variable separable form, here we can easily integrate it and can get the solution. Okay. So, we are going to integrate on the given equation on both sides and putting the constant of integration. We can easily find the integration of the first left hand side term, that will be minus times of log of 1 minus v square is equals to log of x, since integration of dx upon x is log x and constant of integration is as it is. Then we will substitute the value of v, that is nothing but y upon x in the final solution. So, we have y square upon x square is equals to log of x plus c. So, this is the final solution. So, in this way we have learned how to find the solution of the differential equation of first order first degree equations with the variable separation method, and the solution of first order first degree equation with help of the homogeneous equation, homogeneous form method. Okay. So, we conclude with this. Thank you very much.